Hello everyone, my name is Xinyi Wang, and today I'm going to talk about our work on balancing training for multilingual neural machine translation. Multilingual training is a very popular method for many NLP tasks. It is very resource efficient because it allows one to deploy a single model that can handle a lot of different languages. It also allows the performance of low-resource languages to benefit from cross-lingual transfer. However, an important problem with multilingual training is that the training datasets are imbalanced. This is a plot of the number of Wikipedia articles from different languages, and we can see that the languages on the right have far less resources on the language than the language on the left. This indicates that it's very necessary to upsample low-resource language data during multilingual training. A very popular approach by the current multilingual training method relies on heuristic sampling, where one can upsample low-resource language data based on the dataset size. However, this approach is suboptimal because it doesn't consider the relatedness between different languages, and the sampling distribution might be different under different training circumstances. Therefore, in this paper, we want to directly learn the data sampling distribution. In order to do that, we should resort to differentiable data selection, a recently proposed machine learning method to learn the weighting of training data so that the model's performance on separate held-out data is optimized. The formulation of DDS is as follows. Given the training data and the model we want to optimize, DDS learns a separate data scoring function parameterized by phi, so that when using training data based on this scoring function, the model's performance on the dataset is optimized. To optimize the data scoring function, DDS uses a very simple idea. That is, the scoring function should upweight the training data that has similar gradient as the dev data. That is, we can use reinforcement learning, where the reward for a data pair is the cosine similarity between the model's training gradient on this data pair and the model's dev gradient. But how do we use DDS to learn a multilingual data sampling distribution? We first take a look at the existing approach, where a distribution over the training datasets is defined as to be proportional to the dataset size scaled by a temperature term. Inspired by this, we can actually directly parameterize the data scorer in DDS so that it outputs the distribution over the multilingual training dataset. And to optimize the data scoring function, we can use the model's performance on the multilingual dataset as the signal to update the scorer. This leads us to MultiDDS, the algorithm to learn the multilingual training data usage throughout training. To update the model, we first sample a dataset from the distribution defined by the data scoring function, parameterized by phi. And then we do a gradient update on the model using a batch of data from the selected training dataset. To update the scoring function, we use reinforcement learning, where the reward for using a particular training dataset is simply the effect of the training dataset on the model's performance on all languages. That is, the reward is simply the cosine similarity between the model's training gradient and the model's gradient on the multilingual dataset. We take a closer look at this reward signal. Actually, it can simply be calculated by aggregating the dev gradient first, and then take the cosine similarity between the aggregated dev gradient and the training gradient. This is problematic when the number of languages we want to optimize is large. It's because when n is large, the aggregated depth gradient can have large variance, and this can lead to instability in training. To remedy for this problem, we propose a stepwise version of MultiDDS, where instead of aggregating the depth gradient first and then calculate the cosine alignment, we first calculate the cosine alignment for each of the depth set, and then aggregate the alignment. This allows us to avoid high variance in the aggregated depth gradient, and it can potentially help us to avoid the problem where the gradients of different languages cancel out when aggregation. We test MultiDDS on a multilingual TED Talk dataset, and we test it on 2 sets of languages: related, where we use 4 low-resource languages, and each of them is paired with a related high-resource language, and diverse, where we pick 8 languages without considering for relatedness. We test it on 2 NMT settings, many to one, where we train a single model that translates from 8 different languages to English, and one to many, where we train a single system that translates from English to many different languages. Next, we compare the performance of MultiDDS with the heuristic sampling baseline. First, we examine the performance of temperature-based heuristic sampling and sampling based on proportional to dataset size. And we can see that for all the baselines, none of them is consistently better than other baselines. However, DDS is able to consistently outperform the baseline in all 4 settings. It is important to note that the results in the last slide considers the average performance of a multilingual model over all languages. And this is a popular metric that's used by prior work on multilingual training. But this is problematic because sometimes we might care about certain languages more than others. Therefore, we use MultiDDS to prioritize different multilingual objectives. We do this by first optimize MultiDDS on all languages and then switch to a different aggregation method based on the priority. We consider 3 settings: regular, where we always optimize for average performance; low, where we train an egalitarian system that prioritizes low-performing languages; and high, a specialized system that prioritizes high-performing languages. And first, we can comparing the performance of all 3 settings with the baseline in terms of average BLEU score. We can see that MultiDDS still outperforms the baseline, no matter what priority it uses. And next, we compare the performance of low and high for both many to one on the left and one to many on the right. And the languages on the x-axis are arranged from left to right according to increasing performance. And we can see that high performs better on the languages on the right and low performs better on the low-performing languages on the left. This indicates that MultiDDS can successfully optimize for different priorities. Next, we examine the effect of stabilized version of MultiDDS. We plot the reward output from both the standard and stabilized version of MultiDDS, and we can see that the reward signal from the stabilized version has much less variance. And we also run both versions of the algorithm over multiple random seeds and compare the mean and variance of the algorithms. And we can see that MultiDDS using the stabilized reward can actually lead to smaller variance in model performance. So in the future, MultiDDS can be extended to other multilingual tasks other than NMT. And another potential direction is that it can potentially optimize other multilingual optimization objectives other than average performance. Thanks for listening.